Hi, the investigation of this video is based in flying wing drones. The team is made up of Eric Aguirre, David Espinosa, Jorge Heinrich, and Daniel Rios. Here we can see the overview of the video. We will talk a little about the flying wing drone, then we will see the initial sizing of the drones that we chose, and finally all the analysis that we did to get the best flying wing drone of the investigation. The principal characteristic of flying wing drone is that they lack an empennage, so the wing is responsible of generating lift and stability. In order to help with the stability, they normally have swept-back wings configuration, and for wing efficiency, a pusher propulsion configuration. The first aircraft is the Skywalker X-8, a delta-wing commercial aircraft with pusher-type swept-back configuration. The not mentioned is an experimental aircraft designed in a thesis with a pusher-type swept-back configuration. This is another experimental aircraft designed in a thesis with a pusher-type swept-back configuration. The wing trap PPK is a vital aircraft, that is to say with vertical takeoff and landing, but is still considered a flying wing because it does not have an empennage. It is a polar type configuration with an elliptical wing. The FX Buffalo is another delta wing commercial aircraft with pusher type sweatback configuration. The not mentioned 3, this is another aircraft made for a thesis. It is a delta wing commercial aircraft with pusher type sweatback configuration. The Jerry has the same characteristics, but in this one we could see that the wingspan surpasses the limit of 3 meters that we put, but how it is for very little, we keep it in the list. And the last one is the FX-16-1 Phantom, a delta-wing commercial aircraft with pusher-type sweatback configuration. With the measures of all the aircraft, we get these values for average magnitudes. For MAC, that is mean aerodynamic core, we get 0.3216 millimeters. For wingspan, we get 2115 millimeters. And for takeoff gross weight, we get 4.6065 kilograms.
One of the crucial parts when analyzing an aircraft is knowing where that aircraft is going to fly or the air conditions. So in this case, we're going to take the air conditions at a sea level. So in this case, the analysis will be done with a software named XFLR5, and in there, on the type 2 analysis, we'll request the density and also the kinematic viscosity of the fluid. So we are going to see how to calculate each one. So the dynamic viscosity versus the temperature, it has a linear behavior. So by using the general equation of the straight line, we can obtain, so in this case, with this initial data gathered from the book Aerodynamic by the book of Anderson, we can get like sea level air conditions. So it's at 0 meter height. The temperature at 0 meters, it's 288.66 Kelvin. The density of the fluid, we also get it, so we get one right away. It's 1.225. Also, the dynamic viscosity at 0 degrees and the dynamic viscosity at 30 degrees. So in this case, we know that that these will behave on a linear fashion. So by using the general equation of the straight line, we obtain this, so we can get the 15 degrees that we need. So by using this, we obtain that the dynamic viscosity is 1.8 times 10 to the minus 5 kilograms over meter per second. So the kinematic viscosity, we can get it by, it's the division by the dynamic viscosity divided by the density. So in this case, we can do this and we get the result of the kinematic viscosity. So with these two, we're going to plot this, we're going to put these details on the XFLR type 2 analysis. By using the average gathered from the research data that we had from the previous airplanes, and by also using the air conditions at sea level calculated before, we can now generate the type 2 analysis of XFLR5, so we can get the following plots. So we will be analyzing each airfoil for each aircraft that we have. So we have the airfoil MH60, and the thing that with this airfoil it excels is with the coefficient moment, that it's almost minimum. And this is very good because with this type of aircraft, we don't have an empennage. So the stability must come from the wing itself. So by having a low coefficient moment, we can get a very good stability throughout the airplane. We also have the GOE 438 with this one. We can see here like also we have high lifts across alpha and also a low coefficient moment, but not as low as the previous one. We have the S1223. This has very high coefficient lifts throughout alpha, but the thing that this affects us a lot is with the coefficient moments. And with this type of aircraft, we don't really need a lot of coefficient, about a lot of lift. We need a lot of stability because we don't have an empennage that will help it out with that thing. So in this case, this airfoil, it won't be convenient with this type of aircraft. Okay, so for this one, the Sagi 12, we have a coefficient lift that it's decent, but it's not that high, and also the coefficient moment, it's also a good coefficient moment, but it doesn't excel that like the one of the MH60. The one that it has with here is that the coefficient of drag, it's low throughout low alpha or low degrees of alpha, but the overall results of the efficiency of the aircraft, it's low, like it's only like 70, and that's a low efficiency to have. The S7055, on this one, we have high drag on high degrees of alpha, and also we have a lower efficiency, but as we can see here, we have a very good lift, and we can also see here that the coefficient moment doesn't go that low. So yeah, we have very good on these ones. The S5010, so for this one, as we can see here, we have a very low coefficient moments, but with this one, we can see here that the lift is minimum at low degrees of alpha, and also due to this, it will go to stall on very low degrees of alpha. We can also see here the efficiency, it's very low, and the drag, it increases a lot on high degrees of alpha. The MH45, we have the exact same problem like from the previous one. We have a high drag coefficient. We have minimum coefficient of lift, but we can get a very good coefficient of moments throughout alpha or throughout low alphas. The NACA 2412, with this one, it's a very good candidate, but it doesn't excel in anything. Like we have high coefficient lifts throughout high alpha, but we have a higher drag coefficients, so they will decrease our efficiency throughout. And also the coefficient moments, it's decent, but we have better ones. So using all of this information, we gather the following table and we grade them from 0 to 10. So we grade them by using this table, and we will gather the totals so we can decide which one is the best one. So in this case, we know that we need coefficient moments to be a good coefficient moment because we don't have an empennage that will help us with stability, and we don't need high coefficient lift because we are with aircraft that doesn't need that much weight on the structural part. So we don't have a lot of weight, but we need a lot of moment. So in this one, this is the winner that we have. So we choose this one, the MH60, due to the great coefficient moment, due to the great efficiency that it has, and the overall total that it went through. Also, a very good candidate to have is the GOE 438. It's because, as we can see here, it's 8 on every single one. So with this one, it doesn't excel in anything, but it's very average and it's very manageable to have because we can get like a lot of we can go a lot of angles with this type of aircraft. But yeah, I think between these two, these ones are the best that we found to have. But I think that we're going to stay with this one, the MH60, due to the higher score and due to the coefficient moment. So in conclusion, we choose the Airfoil MH60 due to the good overall results of XFLR 5 on the coefficient of lift, the drag, and the moment. In a few words, this airfoil was chosen for the great performance it has during the flight. This is due to the lift and drag values that it can have in different flight stages, and also because of the low moment it has. This is a very good thing to have in this type of aircraft, I was saying, due to the empennage, that we don't have that one. So we will need to get everything from the wings. Okay, so these are the references for every single aircraft. Feel free to search for every single link so you can get more information about every single aircraft.